Hello again. In the last video, we introduced the second law, but all it did was get in the way of us solving the world's energy problem. So what good does the second law do us anyway? The purpose of this video is to demonstrate the inadequacy of the first law, to describe a bunch of observations I know we've all made, and that's going to motivate the need for the second law. Soon after that, we're going to want to become more quantitative about the second law so that it has better predictive value for us. And for that, we're going to need to introduce entropy. Entropy and the second law are some of the most subtle and intricate and beautiful phenomena nature has to offer. And so I encourage you to give yourself plenty of time and patience and opportunity and resources to do what you need to do to try to comprehend these subjects. All right, so I'm going to start with an observation I'm quite sure you've all made, which is that a bouncing ball eventually comes to rest on the ground, even the really bouncy ones. What I'm willing to bet you've never seen is a ball that is sitting on the ground spontaneously start bouncing. And we'll talk about this more, but technically here there is no violation of the first law. A few other observations you've never seen. You've never seen a melted puddle on your kitchen counter reform into an ice cube, as long as you have a decently heated kitchen. You've never seen a drop of food coloring that was dispersed into a glass of water reform into a localized drop of color. But you probably have seen salad dressing unmix, or peanut butter separate from oil. So none of those scenarios I've described offer any violation of the first law. In the bouncing ball, we tell the story that the ball starts with mechanical energy in the form of potential energy from its height and then kinetic energy from falling. And that mechanical energy is dissipated as heat into the mud and earth, and it's now floating around in some random fashion where it just feels too improbable that all of that energy would find its way back into mechanical energy in the ball. So now before we move on, I'm going to suggest that you pause and actually do a calculation that's not related to entropy, but it's just a calculation that's fun to do. And the calculation is to calculate the temperature change in the table that results from dropping a ball on it. So let's say that the ball has a mass of 1/4 kilogram. That's the mass of the ball. Drop it from a height of 1 meter. We'll say that the heat capacity of the wood table is 1.76 joules per gram Kelvin. And let's say the mass of your table is about 20 kilograms. And your job is to calculate the change in temperature of the table. So go ahead and try that. Okay. So the mechanical energy, if we're dropping from a meter, is stored as potential energy. And the potential energy is going to be equal to the mass of the ball times gravity, times the acceleration due to gravity, times the height. Then to get the change in temperature, we're going to use the equation Q equals Cp delta T. And notice that I'm using the capital value. So I'm using extensive quantities, which means I need to account for the amount in this case. And in the story of the bouncing ball, all of this mechanical energy is dissipated as heat. So the assumption you make is that all of this potential energy becomes Q, and that your delta T is now the potential energy divided by the mass of the table. This guy was the mass of the table, times its heat capacity. And if I do out these calculations, I get that the change in temperature was, let me make sure I get the number of zeros right. 1, 2, 3, 4 zeros. 1, 2, 3, 4, 7 Kelvin. Okay, so from this story, I just find calculations like this fun. It's a bit of a sidetrack though. Anyhow, from this story, we're beginning to perhaps develop the idea that different forms of energy are of different usefulness or different quality. So if I had to express that idea kind of mathematically, maybe we could write out an equation that looks something like the useful energy in a system is equal to the total energy minus the amount of energy that is in some disordered or random state that feels less useful to us. We're gradually going to morph this equation-looking thing into the equation that we introduced in the beginning of the class and right before we had spring break. We're gradually going to morph this into this equation, this idea into this equation. And perhaps you already have associations between disorder, the words disorder or randomness, and entropy. But what we're going to do now is give you the tool that you need to quantify entropy. Okay. So before I do this derivation, I want to remind you of a trick that we pulled earlier in the class. Earlier in the class, we were describing a constant pressure process. I just want to remark that I remember moments in the beginning of the class where PV diagrams were really unnatural, and I wonder if you notice how much more comfortable this idea, like what I'm plotting. I don't even have to state anymore that this is a cold temperature isotherm and that's a hot temperature isotherm. So I hope you guys notice your progress that way. I've noticed it in you. Okay, so we pulled this trick for a constant pressure process. We started with the first law. Bella's going to need to bark at the mailman. And eventually, we got to an equation where we said that the heat is equal to the internal energy of the second state. I'm calling this the second state, this is the first state. Plus pressure and volume of the second state minus the internal energy of the first state plus pressure and volume of the first state. These are lowercase. And we decided that it almost looks like the heat for this constant pressure process, it looks like, because these are state functions, it looks like it's equivalent to the change in energy of some state function. And these quantities appeared over and over again in derivations, and so this quantity was given a name and it was called enthalpy. So if you don't recall this derivation, right now I recommend that you pause the video and recapitulate the steps in here. I'm actually not going to review them in this video, but if you find that you're unable to recapitulate these steps, I think this is a good question to bring to our office hours or to email me or to work on separately. Okay. But for now, just recall that we use this trick of identifying when we have groupings of state functions that maybe sometimes it makes sense to call it some other state function. Now I'm going to move on to a completely general process. Actually, let's do a clean sheet of paper just so you know I'm not talking about a constant pressure process. So for any general process, I can rewrite the first law. Solving it for heat. If I make the assumption that we're doing reversible and only expansion work, I can rewrite my work term. I'm going to rewrite the next step. And I'm going to suggest that you pause and make sure you can recapitulate this step. We've done it once before in class, and I'm going to answer the question for yourself. Because I've written constant volume heat capacity, does that mean that we are assuming constant volume? Are we doing a derivation that is only valid for constant volume? So your task is to answer this question and to make sure you can do these steps. Okay. The answer is no, we're not assuming constant volume, even though we have the presence of the constant volume heat capacity. And the reason is because U is a state function. I can choose any path I want to get from point A to point B, or state 1 to state 2. And between any 2 points on a PV diagram, any 2 arbitrary points, I can always find an isothermal and constant volume path to get between any 2 points. So for the next step, we'll assume a perfect gas. But we get a little stuck here because T is a function of volume. So if we wanted to integrate out this term, we wouldn't really know what to do with this. We wouldn't know what to do with this T term. So I'm going to suggest that we divide all of the elements of the equation by T. And what I end up with on the left side is dq over T equals CV over T dt plus R over V dV. And at this point, I can notice something. I'm going to notice something similar that I noticed for enthalpy. I notice that this right-hand side is composed entirely of state functions. And that's going to give us permission to redefine a new state function, and we're going to call it entropy. And there's something that makes intuitive sense. We've already had a connection between entropy being related to heat. And it also makes a little sense that it's related to heat, but scales by the total temperature in a system. That's all for this video. Now, to do any calculation, we can calculate the change in entropy for any of the processes that we've studied, because you already know how to calculate dq over T and derive these equations. So we can calculate ds for isothermal processes, adiabatic processes, isobaric processes, and isochoric processes. But you'll have to be careful, because before, when we were now that we're solving for ds, you'll have to recall that there's a temperature. You'll have to make sure to take into account that temperature is in the denominator, and so when you go to integrate out whichever equation you derive, you have to make sure that you're properly accounting for how temperature appears in that equation.